Everybody get your fucking hands up.
Once again, at this point, you should be very familiar with these three basic kinematic equations. Keep in mind that, in general, position, velocity, and acceleration are all functions of time. But let's look at a special case when the acceleration is not changing with time. In other words, when the rectilinear motion has a constant acceleration. In this case, we can apply calculus and derive three new equations that can be used directly to solve problems involving rectilinear motion with constant acceleration. So if acceleration is a constant AC, and at a time 0, the initial velocity of the object is given as v0, and the initial position is given as s0, then from the equation A equals to dv dt, we can rearrange it to be dv equals to A times dt, which is constant acceleration AC times dt. We can now integrate both sides. Again, choose the proper integration limits. On the left side, we integrate from the initial velocity v0, and on the right side, we integrate from time 0. And after integration, we get v minus v0 equals to AC times t, and it can be rewritten as v equals to v0 plus AC times t. This equation allows us to calculate the velocity of the object at any given time during the rectilinear motion with constant acceleration AC. Note that in this equation, only v and t are variables, v0 and AC are both constants. Similarly, from this kinematic equation, v equals to ds over dt, we can rearrange it. And because from the previous step we have already determined that v equals to v0 plus AC times t, we can just substitute it in and integrate both sides from initial position s0 on the left side and from time 0 on the right side. And we can get this and rearrange it. We get this formula that the position of the object equals to its initial position s0 plus initial velocity v0 times t plus 1/2 times constant acceleration AC times t to the second power. Again, in this equation, only s and t are variables. All the other coefficients are constants. And this equation allows us to determine the position of the object as a function of time. And with the last kinematic equation, AdS equals to VdV, substitute A with constant acceleration AC, integrate both sides, on the left from the initial position S0, and on the right integrate from the initial velocity V0, and we get this formula after rearrangement. As you can see, this equation provides a direct relation between the velocity of the object and its position at the same point. Only v and s are variables in this equation. Therefore, from the three basic kinematic equations, we derived the three new formulas that can be used strictly for rectilinear motion with constant acceleration. Just like what we talked about before, these three equations are not independent. You can only solve for two unknowns with one set of equations between two states. These equations are not difficult to memorize, but if you cannot memorize them, that's fine too. As long as you know calculus, you will be able to derive these on your own based on the three basic kinematic equations by setting the acceleration to be a constant AC. Now let's look at an example. In this example, a ball was initially at a position 1.2 meters above the ground, and it is being thrown straight up in the air. And it returns to the ground after 3 seconds. We need to determine the maximum height it has reached. So at time 0, its position is s0 and its velocity is v0. This is a state 0. And when it reaches the maximum height, let's say this is state 1, it happens at time t1, its position is s1 and its velocity is v1. And later it returns to the ground. Let's say this is state 2, and at this time it is t2, its position is s2 and velocity is v2. Although you might think obviously the initial position of the ball is 1.2 meters, please be careful, because position has to be described within an established coordinate system. Therefore, only after we set the origin point O to be on the ground can we say that the initial position S0 is 1.2 meter. And what we are asked to solve, the maximum height of the ball, is S1. So let's take a look at what we know and what we don't. Here I listed the known coefficients with green backgrounds and unknown ones with pink backgrounds. Particularly, although it was not given in the problem statement that V1 is 0, but we know that from basic knowledge of physics. But there is one more piece of information. We know that in air, the ball is doing free fall motion. In other words, it is only subjected to gravity. Of course, this is assuming that the air resistance is negligible, which is a reasonable assumption in this case. Therefore, the acceleration is a constant negative 9.81 meter per second squared. Negative sign is because the direction of the gravitational force is in the opposite direction to what we established to be the positive position. And now we know it is a problem involving constant acceleration. Don't forget we have 3 equations to use. By examining the known information, it seems that we need to solve this problem in more than one step. There are different approaches, and this is what I did. I applied the first equation between the initial position and the final position and solved for the initial velocity to be 14.3 meter per second. And with this new information, I applied the third equation between the initial state, state 0, and state 1 when the ball was at its highest position, and solved for S1 to be 11.6 meters. And that answers the question. You can try to solve this same problem using a different approach and see if you will get the same answer. And also, if you wish to, you can solve for T1 and V2 as well. And I will leave that to you. Now please answer the following questions.